Okay, so today we're going to be taking a look at LeetCode problem number 33, which is search and rotated sorted array. It is a medium difficulty problem, and this one's actually quite popular. You'll find this one asked in a lot of big tech companies, most notably including Microsoft. This is a really solid problem to study for your coding interviews, so we're going to be taking a deeper look at this one today. So with all that being said, let's take a look at the problem description. There is an integer array nums, which is sorted in ascending order and with distinct values. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index k. Now, k is guaranteed to be between 1 and the length of the input nums, such that the resulting array is nums k plus 1, etc. So now we move on to an example of what rotated means in this context. So for example, we have 0, 1, 2, 4, 5, 6, 7, which might be rotated at pivot point index 3 and become 4, 5, 6, 7, 0, 1, 2. Given the array nums after the possible rotation and an integer target, return the index of target if it is in nums or -1 if it is not in nums. And here's the kicker, you must write an algorithm with O log n runtime complexity. And then as you can see below, we have a few examples. So again, looking at the first example, we have nums equals 4, 5, 6, 7, 0, 1, 2. And in this case, we're looking for a target of 0. So after everything is said and done, our output is going to be 4 because remember, nums is 0 indexed, like all arrays. So it'll be 0, 1, 2, 3, 4. So 0 is at index 4, so that is what we're going to return. And then in the event that our target number is not in our nums array, we return -1, as you can see with example 2 and 3, because in this case, target 3 is not within nums, and again, after everything is said and done, we will not find it there, which is why we will return -1. So to recap real quick, our problem is essentially we're given an array which is sorted and rotated at a random pivot point, and we need to determine if given a target number, is that in our rotated sorted array and at what index? If our target is within nums, then we return that. If it is not, then we return -1. So hopefully all that makes sense. So now we're going to dive into the conceptual overview of this problem. Alright, so let's think of a brute force solution to this problem. So right from the jump, I'm just going to say I don't think it's possible to make a brute force with a runtime of log n. So just to get the juices flowing, let's try and look at our problem and understand what we want to do. So at the end of the day, with this problem is we have a target and we're looking for this target, which in this case 1 in our nums array, and we want to return the index. So in our case, we do have a 1, it's here and it's at index 3. So as far as a brute force solution goes, the quickest and simplest solution that I can think of to solve this problem would just be if we simply did a linear scan of this entire array from the first index 0 all the way to the end, essentially checking each index to see if the value at that index is equal to the target, and if it is, we return the index. And so simply enough, this will work and we will get our answer here of 3. But again, this won't work for this particular problem because we have the added constraint of the solution having to run in log n time. So how are we supposed to look for something in an array in log n time if the array itself is sorted but also rotated? Now again, the rotated part is what makes this problem tricky. But the thing is, knowing that the optimal solution of this problem has to run in log n time actually is kind of a giveaway. Because when you think about it, when you hear log n runtime, what do you think of? The first thing that should pop into your mind is binary search. And the reason why binary search is so useful is because it runs in log n time. Now, log n time is actually really fast. And if you still don't understand what log n means, I suggest you read up on that. But simply put, log n runtime essentially cuts the input space in half every single time. Or in the context of binary search, whenever we search for something in an array, we're cutting the search space in half. So I mean, you can imagine why binary search is so fast, because if we're essentially having our search space every single time, that's half of our input that we don't have to worry about anymore, so we don't even have to look through it. Whereas with O of n runtime, or linear runtime, we're going to have to consider each element in our data structure as we search through it, in the worst case. Now, in the context of this problem, binary search might be a dead giveaway if you understand how binary search works and you just have experience in that. But I want to touch on another subject, because one of the things I want you guys to understand about solving coding problems is that there are underlying patterns for every problem you encounter. Now, the thing is, these patterns might not seem obvious to you at first, but that comes with experience. And for those of you that don't know what I mean by coding patterns, you can kind of think of them like recipes. Kind of like how a chef follows a recipe to cook a specific dish efficiently and reliably, programmers use coding patterns to solve common problems in a structured and optimized way. These patterns are essentially established solutions to recurring challenges. If that still sounds a little vague, let me just use this problem for context. So because we've settled on binary search being our means for a more optimized solution, what do we know about binary search? Binary search is generally a type of search mechanism, or I guess rather search algorithm, that is used on sorted inputs. Generally, you don't use binary search on an input, or an array in this case, that isn't sorted. But in the context of our problem, it still makes sense because it is sorted, it is just rotated. And so the problem becomes, how do we narrow down our search space to ultimately find our target in our sorted but rotated array? But generally speaking, any coding problem you encounter is going to have a pattern associated with it. The thing is, you just have to have the experience and the know-how to be able to identify what that pattern is, and then use it so you can solve the problem in the most optimal way. Anyways, that covers my spiel on coding patterns. But with all that being said, I hope my explanation of binary search makes sense here. Because remember, with binary search, we're having a search space. And so in this case, we can think of our search space being halved until we ultimately find our target index, which holds our target number. So that's the explanation for why binary search is the right move for us to use in this problem. It does everything we need to, and it also checks the box of making sure that our final solution runs in log of n, or logarithmic time. Alright, so now we have a path forward to an optimal solution. So now the question is, how do we implement this? So I'm going to give a walkthrough of how we can apply binary search to our example right here. So first things first, when it comes to binary search, we need to establish our search range. And so the search range will always have left, mid, and right. So left and right will first start off at either end of the array. So left at index 0 and right at the length of nums minus 1. And so this gives us left and right at both ends, which will look like this. Now all we have to do is calculate mid, or middle. And so in order to calculate the middle index, we take left plus right divided by 2. Now this division is going to be floor division because we want to round down. So the way this will look right now is it'll be 0 plus 7, which will just be 7, divided by 2, which equals 3.5. And again, because this is floor division, this will be 3. So our middle index will start at 3. So we'll put mid right here. And so the way I envision this working is we will search for our target with mid. So whatever index mid is at, we will check to see if it matches our target. And I'm actually just realizing this, but the problem is already solved right from the jump. Because as you can see, our midpoint starts at index 3, which holds our target of 1. But to give you guys a better idea of how this is going to work, let me change the target number. So instead, we can change our target. Let me just cross this out. Let's just change our target to 2 in this case. So now with our target at 2, this problem essentially boils down to checking the left and right sides of our search space. So in this case, we'll check from left to mid and then mid to right. And so what we're looking for is we want to determine if our element that we're looking for, our target, is in the left or right search space, and if the search space is either rotated or sorted. Because depending on whether it's rotated or sorted, that changes how we have our search space. Since we're searching for 2, it'll go like this. We'll first check the left half, which is all these numbers. And so we know that left is 6 and mid is 1. And so based off that information, we know that 2 is not in here because while it is rotated, it is sorted in ascending order. And if mid is 1, that means that That means that 2 cannot possibly be between this search space, or in this search space rather. But then if we look at our right search space from mid to right, we'll see that mid is 1 and right is 5. Again, because we know our array is sorted in ascending order, we know that 2, our target, will be between 1 and 5. So we have our search space following this pattern. In this case, what will happen is, let's just move mid out of the way for now, and we'll update left to equal whatever mid was before. Since mid is at index 3, we'll put left here. So again, as you can see, our search spaces now have to focus on this part of the array. So all this right now we can just pretend doesn't even exist. So now we follow the same calculation as before. So now it'll be 3 plus 7 divided by 2. So 10 divided by 2 is 5. So this will be our new midpoint. So we can just move mid right here. And again, the same process unfolds. We first start by checking out the left search space. So between left and mid, we have this right here. So we know that left has a value of 1 and mid has a value of 3. And so if we're looking for our target 2, and again, because I'm going to keep saying this, our array is sorted, we know that if left is 1 and mid is 3 and 2 is in between that, then we know that the target number that we're looking for is going to be in this half of the search space. So like before with our right search space right here, we can actually just completely ignore this. So again, pretend like this doesn't exist. But then we have to update our new search space. So because now we know that our target 2 is going to be between 1 and 3 right here, we have to update mid, or rather we have to update right to be where mid is currently. So let's just move mid out of the way and then update that. So now left is still at index 3 and right is at index 5. So again, following our calculation, 3 plus 5 is 8 divided by 2 is 4. So that means mid will be right here at 4. And so now we have two search spaces. We have 1 and 2 and 2 and 3. But the first thing we want to check is to see if mid is at our target. And it is. At index 4, we have our target of 2. And so in this case, we will just return mid, or index 4 is our final answer. So hopefully this is all making sense. Now I think I want to go for one more example just to really kind of solidify the concept in your head. Because with our second variation, where we're looking for our target of 2, we're only looking at the side that is sorted. I want you guys to see how binary search works when we're looking for a target value in a part of the array that is rotated. So you can still see how binary search can work in this scenario. So let me update all the pointers back to their original positions. Alright, now this time around, instead of looking for target 2, we're going to look for, let's just say 0. As you can see, now because our target is 0, we're going to be taking a look at the rotated portion of our nums array input. In order to more accurately determine if our target is in the rotated or sorted portion of our array, we'll use index 0 as a reference point, and we'll use this initially to compare if it's less than or equal to mid. We always want to start by determining if whatever's at index 0 is less than or equal to index mid, in this case index 3. So as you can see, in this case it would be 6 is less than or equal to 1, which is just not true. And so because we know that the first element of our nums array input is actually larger than whatever our index mid is at, that tells us that we are looking currently at the rotated portion of our array. And so because of that, we know that our target of 0 is going to be in this half of the array. And so we need to calculate our new search space. And so because of that, we'll move our rightmost boundary, or our rightmost index, to where mid was at first, right here. And then we do our calculation. 0 plus 3 divided by 2 is 1.5. Because it's floor division, it'll round down to 1. So we know that our midpoint is going to be right here at 1. So in this case, 6 is less than or equal to 7. And so now because we know 6 is less than or equal to 7, that the boundaries of left and mid cannot possibly contain our target of 0. So again, we have to update our search space. And so the way it works for updating our search space for our leftmost boundary is that it is mid plus 1. Because in this case, we also know that mid is not our target of 0. So left will be updated to mid plus 1, or in this case, index 2. So we can update that real quick. So left will be right here at index 2, and right will be at index 3. So again, we have to calculate our midpoint, which is 2 plus 3 equals 5 divided by 2, floor division, which will then put mid also at index 2. And so as we begin our iteration, the very first thing we should check is to see if mid is equal to our target of 0. And in this case, finally, it is equal to our target of 0. And so because of that, we know that the final answer for this variation of the problem will be 2. So we return 2 as our final answer. So this is essentially how we solve the problem search in a rotated sorted array. We leverage the power of binary search to be able to look through our rotated sorted array to be able to pinpoint the index of our target that we're looking for. I really hope so far my explanations have been making sense, because now the next step is to implement this in code. So if it doesn't make sense now, hopefully when I explain it line by line, it'll start to make more sense. So with that being said, let's go to the coding portion of this tutorial. Alright, so now let's code out the optimal solution. So the first thing we want to start off with is we want to initialize the boundaries of our search space. So initially that's going to be the entire array nums itself. So remember, we have to have left and right. So that's pretty straightforward. Left will start at index 0, and right will start at, will be length of nums. So this gives us a starting point from which we can start doing our binary search and having the search space and then updating either left or right accordingly. And so pretty much all binary search problems start like this. You start by defining left and right, and then we'll enter usually a while loop where we'll say as long as left is less than right, then we continue doing this. So now we can write the logic in the while loop. And again, all binary search problems start by doing this. We have to calculate the midpoint. So there are a couple of calculations that you can use, but the safest one that we can rely on is left plus right minus left divided by 2. This will always give us the midpoint of our search space. And this is crucial. This is why we calculate it very first thing in the while loop. It's the first thing we want to know. We always want to keep mid updated. And so pretty much after this is when we start entering conditional logic. If certain logic is fulfilled, then we look in the left search space, and if it's not fulfilled, then we look in the right search space. Now this can vary between different problems, but generally speaking, all binary search problems will start off something like this and then have conditionals. So now we have to define our conditionals so we can properly have our search space. Well, actually, taking a step back here, the first thing we should do is actually just do a little check to make sure that the midpoint is equal to our target, because then we can break out of this while loop early. So simply put, that would just be if nums mid is equal to target, then return mid. So if we ever enter this conditional, then we break out of the loop and return mid, and that concludes our problem. But we should also handle the case where if mid is never equal to our target, then we have to return -1. And so we'll do that after we've exhausted our search by breaking out of the loop and just returning returning -1. So that's outside the while loop. So now all we have to do is figure out our conditionals to have our search space. So basically our search conditions boil down to if nums left is less than or equal to nums mid, then we do something. Otherwise, we know that we need to update something on the right side of our search space. So we can easily translate that as nums left less than or equal to nums mid. So we start by checking the left half, or we check the right half. So let's leave this blank for now because we need to do the other half, which is just else. We only enter this if we know that nums left is less than or equal to nums mid. In other words, if the right part is sorted and the target is in that range, then we look to the right. So in this case, if we enter the else part of the statement, we want to check if our target is between index mid and right. or right minus 1, because remember it's 0 indexed. So that'll look like this. Nums mid is less than target, which is less than or equal to nums right minus 1. The minus 1 is important here because otherwise we'll get an out of bound error, which will crash our program. And so what do we want to do here? If this condition is true, then we need to update the left boundary to be equal to mid plus 1, because we know that our target is going to be in the right half, and so it's going to be past mid. So we update it accordingly, so left equals mid plus 1. Otherwise, if that isn't the case here, then we have to update the right pointer to be right equals mid, because we know that it's not in the right half, so we can discard that and update update right to where mid is currently. So that'll be simply right equals mid. So now let's focus back on the original conditional up here, nums left is less than or equal to nums mid. So we do something similar here. Again, we start by checking if the target is between nums left and nums mid. So we can easily translate that as nums left is less than or equal to target, which is less than nums mid. And so if this case is true, we simply want to update right to equal mid, because then we know that the target is between nums left and nums mid, and so our right boundary needs to be updated to where mid is currently. So that's how we get right equals mid. Otherwise, we need to update our bounds, or left bounds, so left equals mid plus 1. All right, so this should pretty much be it for this problem. Let's do a quick run through. So remember, with binary search type problems, we always start by defining our left and right boundaries, and then we enter a while loop, which is usually defined as left less than right. Because as long as the leftmost boundary is less than right, we have a search space that we can have and look through. Then we must calculate our midpoint. This is the first thing we have to calculate. It is one of the most important things because we have to have a frame of reference. And also mid gives us a way to update either our left and right boundaries. Then we have a check here. This just lets us exit the problem if we ever find our target. And then all binary search problems will have their set of conditionals like so, which pretty much is the hardest part of writing out binary search problems because you need to know what your conditionals are. In our case, because our input array nums is sorted, but it's also rotated. So we always want to check if our leftmost boundary is less than or equal to mid. This lets us know if the left half is sorted. In the case the left part is sorted, we want to know if our target is within that range. If it is, that means we can shrink the search space, which means changing the rightmost boundary to where mid is. Otherwise, we update our left boundary to mid plus 1 because we know our target is not within that search space. And so when we're not checking the left half of our search space, we check the right, and we do the exact same thing pretty much, where we look to see if our target is within the right half of the search space, so in between mid and the end of the array, or right minus 1. If it is in the right half, then we have to update our left pointer to equal mid plus 1 to shrink the search space so we can focus more on the right half. Otherwise, if that's not true, then we know that our target is not within the right half of the array, so we can shrink the search space by making right equal mid. And then if all of this fails and we don't find our target, we just simply return -1 like the problem told us to. So hopefully all that makes sense. That's pretty much how you solve search and rotated sorted array, LeetCode problem number 33. I hope you learned something today, and I really hope the main takeaway you got from this video is the pattern binary search. Now, usually this pattern is referred to as modified binary search, but in any case, it's still an important concept to understand, and always make sure that when you're reading a problem, if the problem gives you a sorted input, like an array of nums that's sorted in ascending order, that's usually a pretty good giveaway that you should start focusing your efforts on binary search, especially if it asks you to find a certain value or index within that sorted array. The reason why I keep talking about coding patterns is because I do firmly believe that they are the best way to prep for coding interviews. If you can find out which patterns to focus on, then solving coding problems like this in interviews become a lot less daunting, because as long as you can identify the pattern that the problem is using, solving it becomes a lot easier. Which is why if you're interested in learning patterns like this and many others, check out techinterviews.io, We're a comprehensive interview prep course that covers everything you would need to know for your next coding interview. That includes coding patterns, data structures, algorithms, behavioral interviews, salary negotiation, and more. If that sounds interesting to you, please check out techinterviews.io. Anyways, with that being said, I hope you learned something, and I'll see you in the next one.